communication course, maybe for a moment. And so what's going to happen with my nonlinear state space model? Two things are going to change, right? K is going to be gone, right? Because we have these time homogeneous increments. Because this F defines the increments. So that's one thing. We're going to get rid of time. What else, everybody? Over here I said it's an independent sequence. What will I assume here to get time homogeneity? Come on. Independence, it could be 0, 0, 0, 0, a Gaussian with variance 100, 0, 0, a Cauchy, 0, 0 exponential, what? ID, thank you. I just want somebody to say it. And there we've got it. So that's a state space model we all would like. And now you see there's a big data compression. In order to describe the model, I have to tell you the dynamics, F, and I've got to tell you the statistics of the noise, the disturbance that drives this process. So you get this complete collapse in model complexity. Well, you start with some crazy stochastic process. Now you've got something simple. Now, we shall see. Yeah.
It's like a very basic question.
Yeah.
What I still want to ask is because the whole point of stochasticness here comes if you knew X0.
Yeah.
Okay. The only other part which is probabilistic is NK, right?
Yeah.
Okay. So.
Yeah.
And you always keep saying like before. I think it's Kohlmeier point of view where if omega is given, then the whole thing becomes determined.
Yeah, because if omega was given, then the sequence nk would be known from now to eternity, and so you'd know x from now to eternity. Yeah, yeah, and so that's the goal of filtering and all that, is to try to get more and more information about omega, so you can predict the future better. Yeah. Yeah. Okay. All right. So the next step. So this is like, I hope. How many of you have seen Markov chains before? Nobody? Good. Yeah, you did, yeah, okay. It's sort of not a very conventional way of presenting it, because usually you just presented this boring transition matrix, and you get these little diagrams with, but it's a state space model. That's the first thing you should know. Just bake that into your heads. So for a time homogeneous model, we don't have to think about, well, you could see here, I might as well take, just this equal to 0. So, looking at it just jumps and so forth. I'm about to get to your answer. I don't need, just like here, I only need to know the distribution of n and f. I don't need to know these transition probabilities for every increment. I only need to know them for one jump. So that's when you get what's called the transition kernel. Yes. And that is defined as follows. It's just what you're seeing here. All right. So for all x and All right. So if you have a representation like this, you need to know the distribution of n and you need to know f. Often that's not given to you, and you have this instead. You have, for every x, you have a probability measure on b. And it's really helpful to start off general. So this, again, b could be the Borel sigma algebra Rn, for example. Or it might be a finite state space, in which case there's any subset. We just assume it to be any subset. Okay. Cool. So I am going to torture you a bit. So I'm going to, maybe we should give an example or two first, but then I'll torture you. So the classic examples. Linear state space model. Okay, that's a Markov chain, right? And WK's ID, that's all you need. I've changed the notational convention from Hayek's book. So I've written k plus 1. Because I hate putting a k there because this is new noise, you know. So I'm going to, just tweak things there a bit. Just like here, I've got this new noise entering the system, which is independent of xk. So what's its transition probability? So this is a Markov chain where x is Rn, and B is equal to the Borel sigma algebra on Rn. And let's work it out. What's the probability going from x to a? It's this monster here. And you have to stare at this and you have to plug in what x of t plus 1 is, and it's given right there. All right, and I apologize. I see I'm doing parentheses sometimes and subscripts other times. Sorry. And what's that, everybody? W's ID. X0 is given, okay? X0 doesn't depend on the future. So, this would not be a Markov chain if X0 was a function of all the noise, all of the future. So X0 is independent of all the W's. Sometimes you use that expression for independent. All right, what is that? Well, x of t equals x. You can imagine you can just say x of t equals x here, right? But this guy here is completely independent of x of t. So there's no, it's just an ordinary probability. And there you have it, Should we, we could write that as an integral if W has a density, or a sum if W is discrete, or whatever it is. But we can write it as the integral of the indicator function that fx plus W is in A. I can't use an F. So this would be this if we had a density, if W had a density. I know Hayek writes f sub W, but I've got an F over there, so I'll use P sub W. All right. All right, so it's an integral if there's a density. Again, if W is discrete, it'd be a sum. That's what it is. All right, cool.
So is that just a scalar? Because you don't have is it FK or?
Well, it's a probability, right? Now, hold on a second. Now we've got it. So we've got the model, which I claim is a Markov chain, because I've made a claim that any process of that form is a Markov chain, which we could verify later. Maybe maybe that's homework. But no, what's your question? So then we've got the transition probability, which is a probability, conditional probability. So it's a number between 0 and 1. And in this case, and it's always the same form. I mean, I've done this for a linear model. If it was a nonlinear model, you would just plug in the nonlinearity here, and that's it. Say it again?
If you just had the model xk plus 1 equals f times xk.
F times it. Oh, without this, yeah. Yeah. That'd be a Markov chain.
So if you did this, it would be as if you're recasting just the regular dynamic system as a Markov chain.
Yeah, and it's useful sometimes, believe it or not. Deterministic, thinking of a state space, a deterministic state space model as a Markov chain is sometimes a useful way of thinking. Yeah, and you can imagine if this was 0, then this again would just be a indicator function that WK. It's a point mass at fx.
I mean, in that example, if you knew initial condition, then you know everything.
No way, no, come on, IID.
No. I'm saying if for the
Oh yeah, sure. Oh yeah, for a linear state space model without noise. Yeah, if there's no noise here, it just propagates. Yeah. Absolutely. Yep. No, but it's still, it comes, I mean, in control, we almost always ignore noise. Yeah. All right, so that's one standard example. The other is a reflected random walk.
So you're calling that 2-argument p-function the kernel?
What's that? So you're used to thinking about transition matrices, but when you've got something like Rn for your state space, then you have to look at it as a for every x, you have a probability measure.
For every a, that's a subset of 4L?
No, for every x, you have a probability measure.
No, I'm asking about what you're calling the kernel 2-argument p-function?
Yeah. This function of x and a is called the transition kernel. That's what it's called. Yeah. You say kernel instead of matrix. It's just that's what it is. Yeah. So it's a kernel is a function of two variables like this. On the left, it's x in some state space, and a is in some sigma algebra. I'm not responsible for that language. I don't know why it's called a kernel. Yeah. But it is, when you talk about kernel methods, it's exactly the same thing. I mean, kernel methods, you're assuming you've got something like this, but it's got a density. So, in fact, see, we see here, forget it. Forget it. There's so many things to say. So the other example is a reflected random walk. Yes? No, it's good.
So A is just a set.
It's any set. I want to be able to ask any question. So, for any set A you give me, at least that is admissible in this sense. I want to be able to know the probability of in one step jumping into that set.
So it's a sequence of states.
No, set. Come on. No, come on. I have a state here, x, and that's where x of 0 is, right? And then x of 1 is somewhere, I don't know. And then I have some set A, and here x equals R2. And I want to ask the question, in one step do I get into that thing? What's the probability? I'm asking the question, am I going to end up there? Well, to answer that question, there's a probability. It's a probability of going from x to a if this is equal to a. That's equal to x. Yeah.
So we're saying that x is a state, but we're not trying to answer the question what is the next state. We're trying to answer the question where the state belongs.
Yeah, that's all we can answer, because the probability, typically, like in this example, where there's a density, if we ask what's the probability of going from x to another state, it would be 0. If there's a density, if you say what's the probability of fx plus w equals y, and say w is a Gaussian, here w is a Gaussian variable, we know that'd be 0. Yeah. That's why we have to introduce this language.
So can we make the set smaller and smaller so that we can estimate the state?
No, we can't. You can imagine, just like probability measures, sometimes there's a density, and so you can talk about the relative probabilities. That's all. Yeah. Yeah. Well, no, it's typical. You know, a Gaussian or an invariable, what's the probability that a Gaussian invariable is 0? It's 0.
Yeah,
What's the probability it's pi? 0. Probably any number.
that's not really acceptable in most applications.
No,
To
the
say,
whole...
like, the set is the whole room.
It's not the whole room. A could be small. No. The diameter here could be a nanometer. I just got your microscope. No, it's any A. We want to ask this question for any set A, which in this Borel segment, and this in B, yeah.
So we can make it.
No, come on, you're questioning the entire course now. Let's do that another time. The whole course is based on the premise that we have probabilities of events, and we can't know for certain whether it will be a single point. Yeah.
Exactly.
Okay. Yeah, I can kill all this. Yeah, so let's make it simple. Just the simplest. So first, I'll write everything down. So I've got my state space. It's easier here. It's just 0, 1, 2, and so forth. So it's just the integers, the non-negative integers. And my probability of going from x to x plus 1, we're going to call that alpha. So we're really given just one parameter. We're given a parameter alpha, and then we just define mu to be 1 minus alpha. And this is called a reflected random walk. So basically, wherever I'm now, I jump up with probably alpha, or I jump down, probably mu, unless I'm against the wall and I can't go down anymore. All right? And let's stare at this for a bit. First of all, is it of this form? Well, you're just going up or down, and it's all completely homogeneous. This isn't just time homogeneous, it's spatially homogeneous. So whatever x is, as long as it's not 0, the dynamics are the same. It's the most boring Markov chain in the world. You know? And so you can write this as, of course, it's going to be xk plus an increment. All right? Where that is 1 and minus 1. But the problem is that if you do that, you could get negative. So this is going to be IID. Remember I said this was IID. It can't depend on xk. It can't suddenly decide it'll be 0 when xk is 0. So you just have to put a plus sign around that. So the plus means like very common notation to stick a plus in there. Just the maximum of the argument in 0. So this is the state space model associated with this boring reflected random walk. Yep.
I'm sorry, it might be a stupid question.
Yeah, no, please.
Did you say that the probability of going from one state to the next would be?
Yeah, I did.
Then how did you define it?
In general. So here I said, like, if I had a Gaussian distribution, I'd have a problem. So here, in this example, if I'd started with this, and I assume this was Gaussian, I'd have that problem. So if this was Gaussian, there would be a probability of hitting 0, you know, because there's a probability that this is more negative than that. And so you can be 0. But there wouldn't be a probability of any other, the probability of any other state would be 0. Oh. All right. And you can plot this. And let's go in and think about this thing for a bit. Let's take x0 really large. That's for the fun of it. That's an integer. I haven't put any constraints in this thing. And let's assume that alpha is less than mu. Oh yeah, that's right. I didn't tell you what delta is. I mean, you could have guessed, right? I mean, obviously, if we be consistent with this, with probability alpha, we go up, so delta equals 1. With probability 1 minus alpha, which is mu, we go down by minus 1. And then if this was 0, I'd get minus 1 plus is 0. So there it is.
So we only have two possible states we can transition to.
Yeah, this is a really boring model. Okay, but actually, by the way, it's called the it's a version of the MM1Q. It's a discrete time version of the MM1Q. So it's a standard model in queuing theory. But imagine, why would I make it such a big initial condition? It's because I don't like this plus sign. I like linear systems. And so what would happen if I had such a big initial condition that I'd have xn would just be x0 plus, oh, well, let's just do this in stages. So this is true, I can iterate. And in fact, we can only go down one step at a time. So that plus can't kick in until after 10 to the 10th samples, right? You know, all right, I mean, these deltas are plus or minus 1. So I'd have to hit 0 in a short time, I have to get a lot of minus 1s, you know. And the minimum number is 10 to the 10th, so I have to wipe out the initial condition. All right. So this is true for n less equal than 10 to the 10th for my initial condition. Now, why would I make it so big? Is because I can think about averaging. I know that when I average this, the law of large numbers holds. So put it like this, you know, multiply and divide by n, and we know this average converges to the mean. And the mean is what? You know, it's a discrete distribution. It takes on the value 1 and minus 1. So it's 1 times the probability of that times minus 1. So I wrote it out. It's 1 times the probability of being 1, minus 1 times the probability of minus 1. That's what I called alpha, and that's what I called mu. And so that's why I assume that mu is bigger than alpha. That means like it's a negative drift. You see that this thing is just drifting downwards. So if you plotted this as a function of n, and there's x0, and x0 is 10 to the 10th, everybody. That's 10 to the 10th. And the noise is size 1, and that's 10 to the 10th. Do you think it makes any sense to wiggle? A wiggle, the wiggles is size 1. That height is 10 to the 10th. If you plotted this, it would look like a straight line. with this slope being that's because of this absurdly large initial condition, because I'm compressing space, I'm compressing time, so all the volatility disappears. All right, and this is known as a fluid model. So the fluid model is another wonderful trick in queuing theory, is to basically take the stochastic model and just use this insight and say, forget stochastics, let's look at the deterministic, core behavior. Of course, that's only an approximation for large initial conditions. If you zoom in, and say you start with an initial condition of 10, then you're going to start, 1 is not that small compared to 10. It's only 1/10 of 10. And so you'll see wiggles about that big, and you're going to see a bit of wiggling around, and it'll bounce around. Like that. That's it. Now, it's amazing that such a simple process actually has some really exotic behavior. You can take you could kind of read a whole book that big called The Single Queue. And people have ruined their lives studying this little system. So it's boring looking, but it's actually, there's actually some pretty math behind the scenes. This one out of batteries, that'd be cute. I think I ran out of batteries, but that's fine. No. Okay. So, I said I'd torture you, let's do it. So, you can see that this is a stable system. In the most basic sense. I start out at some gigantic number, and I reach the origin. And once I reach the origin, I chatter around, and I never blow up again. It's stable as hell. So what I want to do is actually, even though you've only been looking at Markov chains for 40 minutes, just jump into stability theory. And who was it? Was it you who talked about stability in generators? And yeah, all right. So blame this guy. Maybe this one. So a typical question you could ask. Yep.
Just a quick question.
Yeah.
So this model completely doesn't capture what you are stating there, right? Because P of 0, 0 equal to mu, delta can never take 0 there, right?
That's why I put the plus sign in. So imagine if xk is 0, then this takes on value -1 with probability mu, right? So the inside would be -1. But the plus means I take the maximum of 0. So -1 gets hit to 0. So this is exactly the same as this. Yeah? Okay.
What does P of 0, 0 equal to mu mean? So if it hits 0, then...
No, it means that what's the probability, if I'm 0, what's the probability of staying still?
Oh,
Yeah, that's all. Yeah. Yeah, so here my sets A are just have to be points because I'm in a discrete space. I might as well look at points, right?
Won't it make sense to have P of x, x tends to 0, 0?
No, but it's not true. No, this isn't allowed to stand still unless it reaches the origin.
Only at 0.
Yeah. This example, I made the simplest example just to make things easy.
So then you cannot stay at the same state.
Anywhere else except 0.
Except
Yeah. This is a very special case. So in general, a reflective random walk can take on arbitrary large increments, and it can stay still with positive probability. It's just
that. So
What's
if
that?
it was x, x, then this is not true.
Yeah, it's only at 0. Yeah, that's why I wrote here x greater than equal to 1. We allow this. But if we start at 0, we can't go down. So, yeah. All right. Okay. So for a control audience, there's about 20% of you. A basic question is like, is some sort of, we want to understand not just stability, like it doesn't blow up. We want to get some idea of we have some cost function, and we want bounds on performance. So here's a stability question, or so B measurable, it's, That's right, my God. I shouldn't be so abstract. Maybe we should make this Rn. Oh, I'll just say it. Nah. Who cares? You can ignore that. In the end, we're going to take a continuous anyway. X is going to be Rn, we'll take a continuous. Just ignore that. But I just, for my own benefit, I have to say it. We'd like to look at the expectation of C of xk and say, is it bounded? I mean, is it less than or equal to some bound for all k? Does it converge? And I'll give this a name. Let's call it like eta k. That's the expected cost at time k. Forget the initial condition. Let's just ignore that for the moment. Maybe it converges. And it's not just one function. We'd like to be able to say this for a whole family of functions. Okay, so does anybody remember stochastic differential equations in the homework? So remember you had a differential equation for the second moment. So basically, we'd like something like this. So we did this in the homework. You did this for continuous time. You basically came up with a differential equation for eta t, because this xt was continuous time. Can we do the same thing in discrete time and more? And yes, we can. And it turns out that generator that we looked at for stochastic differential equations has a counterpart here. So. So the main tool, and I can say that because I wrote the book on this. I mean, that book I mentioned with Richard Tweedy, the whole book is about Lyapunov functions and answering these sorts of questions. The entire book is really about that. And it's about and the generator in this context. All right, so let's go and do it. So I claim that in 10 minutes I can give you a result that you'll all be satisfied with. Right now it's my clock says it's 4:11, so that means 4:21. Let's make it 4:25. I don't know. But you can stop me. Actually, we need this. We need that. So somebody tell me, what do I mean by the generator? I told you it wasn't continuous time. What should it be in discrete time? Yes, difference. So for the SDE, we had dH of x was equal to ddt of the expectation of h of xt, evaluate t equals 0, and with x 0 equals x. All right, so burn that into your brains. You will need to know that next week. You know, and that turned out to be equal to something pretty, right? It was equal to, you know, it was equal to something. It was a second-order differential operator. All right. Now it's much easier here. It's differences. So for a Markov chain, let's do the same thing. dH of x will be the expectation of h of x t plus 1 minus h of xt. So instead of a derivative, it's a difference. Given xt equals x. Right? And you can write this out in an abstract way, right? Because this, we have a